Chapter 15, Properties of Gases. This lecture will help you understand Charles's law and Boyle's law. An ideal gas is a hypothetical gas that perfectly fits all the assumptions of the kinetic theory of gases. The kinetic theory of gases states, gases consist of a large number of tiny particles that are far apart relative to their size. Most of the volume occupied by a gas is empty space. This accounts for the lower density of gases compared with that of liquids and solids. It also explains the fact that gases are easily compressed. Collisions between gas particles and between particles and container walls are elastic collisions. An elastic collision is one in which there is no net loss of kinetic energy. Gas particles are in continuous, rapid random motion and possess kinetic energy. There are no forces of attraction or repulsion between gas particles. You can think of an ideal gas molecules as behaving like small billiard balls. When they collide, they do not stick together, but immediately bounce apart. The average kinetic energy of gas particles depends on the temperature of the gas. An ideal gas is defined by four physical characteristics: its volume, pressure, temperature, and the number of atoms or molecules. Volume is measured in liters, cubic meters, or cubic inches. Pressure is measured in pascals, atmospheres, or pounds per square inch, and must be absolute pressure, not gauge pressure. Temperature is measured in Kelvin or Rankine. The number of atoms or molecules are measured in moles. One way to specify the amount of substance in a system is to give its mass. Another way is to measure the amount of substance in moles. 1 mole of a substance is 6.02 times 10 to the 23 basic particles. The basic particle depends on the substance. Monatomic gas means the basic particles are atoms, such as helium. Diatomic gas means the basic particle is a 2-atom diatomic molecule, like oxygen. Triatomic gas, the basic particle is a 3-atom triatomic molecule, like water. For most of these problems, we will assume the number of moles of a substance remains unchanged. That is, there is no gain or loss of the number of basic particles in a gas. Jacques-Alexandre Charles was a French mathematician, physicist, and inventor. He experimentally found the volume of a gas varies directly with the absolute temperature at constant pressure. If the volume of a gas increases, then the temperature must also increase. If the volume decreases, the temperature must decrease. Another way to state this is, if the volume and temperature of an ideal gas are allowed to change at constant pressure, then the initial volume divided by the initial temperature must equal the final volume divided by the final temperature. Temperature must be measured in Kelvin or Rankine. V over T is equal to a constant. If we call that constant m and multiply both sides by t, we find the equation of a straight line. Under Charles's law, the volume changes linearly with temperature as long as the temperature is specified in Kelvin. We will not be concerned with the actual value of the constant m. Construct a container with a tightly sealed, movable piston. The piston is able to respond to temperature changes. If the gas in the container is heated, its volume expands. The piston moves if there is a pressure difference. There is a force acting on the piston, and the piston moves until the external and internal pressures are equal. This is the constant pressure process. If the gas cools, the volume must decrease. At 40 degrees, some helium occupies 15 cubic feet. What will be its volume at 90 degrees Fahrenheit? Our data are the initial volume, initial and final temperature. We do not know the final volume. Since there is no mention of a sealed container, we will assume a constant pressure process and can use Charles's law. We have to convert the temperature to Rankine by adding 460 degrees to the temperatures. The basic equation is Charles's law. The working equation solves Charles's law for the final volume. Substituting what we know yields a final volume of 16.5 cubic feet. A tank with 500 liters of propane is heated from 17 degrees Celsius to 31 degrees Celsius. What is the new volume of the propane in the tank? Our data are the initial volume, initial and final temperature. We do not know the final volume. We assume a constant pressure process and can use Charles's law. We have to convert the temperature to the Kelvin scale by adding 273 to the temperatures. The basic equation is Charles's law. The working equation solves Charles's law for the final volume. Substituting what we know yields a final volume of 524 liters. Robert Boyle was an Irish chemist and natural philosopher and is considered the father of modern chemistry. He experimentally found the pressure and volume are inversely related at constant temperature. If the pressure increases, then the volume must decrease. If the pressure decreases, the volume must increase. Another way to state this is that if the pressure and volume of an ideal gas are allowed to change at constant temperature, the initial pressure times the volume must equal the final pressure times the volume. The chart shows a relationship between volume and pressure under Boyle's law. It is an inverse relationship. If a pressure of 1 atmosphere is exerted on a volume of 1 liter and is then increased to 2 atmospheres, then the volume decreases to 0.5 liters. If the pressure of 2 atmospheres is decreased to 1 atmosphere, then the initial volume of 0.5 liters must increase to 1 liter. Some nitrogen at a pressure of 110 kilopascals occupies 185 cubic meters. Find its pressure if its volume is changed to 225 cubic meters. Our data are the initial and final volume and the initial pressure. We do not know the final pressure. We assume a constant temperature process and can use Boyle's law. The basic equation is Boyle's law. The working equation solves Boyle's law for the final pressure. Substituting what we know yields a final pressure of 90.4 kilopascals. The mass density is the mass of the object divided by its volume. Using the mass density, Boyle's law can be rewritten. And we find the initial pressure divided by the initial density is equal to the final pressure divided by the final density. Some carbon dioxide has a density of 3.75 kilograms per cubic meter at 815 kilopascals. What is its density if the pressure is decreased to 725 kilopascals? Our data are the initial density and the initial and the final pressure. The basic equation is Boyle's law with density. The working equation solves Boyle's law for the final density. Substituting what we know yields a final density of 3.34 kilograms per cubic meter.